Greetings, everyone. I'm Sharif, and this is Group 9. We shall be taking you through our explainable AI for our models. Our topic is about constructive self-supervised knowledge distillation for real-time public identification with conditional awareness. So the aim was to, the key focus were performance gap, failure modes, and the architectural solutions. Taking to our first slide, this talks about explainable AI, which is a process that enables us to understand and trust products created by machine learning algorithm. In our case, here we're referring to our models, whereby can be able understandability is all about understanding the characteristics of the model to make a human understand its functions. And compressibility, this refers to the weight of this algorithm to represent its learned knowledge in a human understandable manner. Then interpretability is to explain the meaning of the meaning in understandable terms to a human. So, and explainability, this is associated with explanation as the interface between humans and the decision makers. So, ideally, it's all about understanding why this model came up with this decision, the kind of features it used before coming up with a solution to our project. For the models that we used, one we applied the best models and ones of that were the models which did perform well, we were two that we applied for the explainable AI. And on the graph, it just shows you how the model performance, how it was with our teacher model and foundation transformer model being the best. Then the VAE, that is the Bokomoto decoder and constructive model, being the worst performing models. The teacher student model achieved the top accuracy of 96.8%. And the metrics that we are looking into is accuracy and interpretability, how these models came about to make these decisions. And these are a few metrics of how our models were. The performance, the teacher model, the foundation model, the ability, the constructive will to break model. The dark lines, like how you can see that, then the light blue, maybe it is representing the training accuracy, then the dark is representing the validation accuracy. These are the metrics which we use when we are training these models, and the graph just represent a visual of how they were, how they performed. And so the technique, the explainable AI technique which we first applied was SHARP, which is a technique that is based on the game theory that helps interpret machine learning models prediction. It assigns features as an importance score, then quantifying the impact of the models input. For our case, SHARP was used to analyze the feature inputs across the models and understand how the different characteristics contributed to the prediction. The characteristic which we are looking into, we are looking into the harmonics, we are looking into the features, the fundamental frequency, the MDI, and the rest. So the analysis does explain why the model makes a certain prediction and guides the features, selection, and model improvement for real-time public identification. So this is some of the visual for the SHARP, and our features which we have a pitch, the various harmonic and command. You can see that for the best two performing models, and these features were very high, which does explain to why they were giving us that score, the score being above the rest of the models. So this is a video trying to explain or trying to show how these features really for the model to come up with that decision. Thank you. I hand over to my colleague to take you through the next part.
Thank you very much, Mr. Sharif. So our second technique we applied, it was the GradCam XAI technique, which is the gradient weighted class activation mapping. And it's an explainable AI technique used to interpret our deep learning models, which highlights the important regions in an input that influence the model's predictions. In speech recall processing, or where we are determining our vocal key, this breadcrumb was applied together to the spectrograms to identify which frequency time regions contributed most to our model's classification decisions. And then the feature importance for vocal key identification, where the models classify vocal modes, which were the modal, falsetto, breathy, and pressed, using the acoustic features. Broadcom highlights which acoustic properties of spectrograms and regions influenced each prediction. And then we applied the back propagation of gradients, where it computes the gradients of a specific class score with respect to the features, to the feature maps in a convolutional layer, and then weights the activation maps to visualize the most influential regions. And it was also used to generate heat maps to overlay onto the input, show which frequencies and time frames the model relies on. So in our system, these highlighted regions correspond to the pitch for months. So as you can see, using RedCam, we managed to generate the error patterns from our illustrations, where we illustrated the teacher-student model confusion matrices, the phonation aware transformer, then the VAE model confusion matrix, and the contrastive verb to vector model confusion matrix. So the key error in our teacher-student model is that, as you can see from our illustrations in the top left, the falsetto and the breathy confusion, whereby the error rate was 5%, and the root cause is due to the distilled knowledge. It preserves the high frequency cues. And then in our phonation, the falsetto and breathing confusion was 15% due to the attention mechanism limitations. And then in the VAE, it is 18% due to the shared latent space for energy entropy features. Plus, and then in our contrastive verb to vec, the error pattern, it had the multiple error types, and it was greater than 20% due to the task misalignment issues of using the web to vec already pre-built model. So so our improvement pathways, we have optimal performance, whereby hybrid architectures, which will combine all these strengths without relying on one model. Then for contrastive models, we add pitch shift augmentation to increase accuracy. And then for the VAEs, adversarial discriminators to improve the separations, and foundation specific projection head for the foundational improvements. And as you can see, all these are aimed at amending these key error patterns. And so in conclusion, the teacher student, which had 86.8%, and it was the optimal choice during our MLabs. And then best interpretability, it was the foundation transformer, which provides valuable attention maps for understanding decisions. So we are then avoiding the vanilla VAE, which focus on harms on discrimination. And then the future work is hybrid architectures, combining distillation plus attention mechanisms, which were actually applied in our final models. Thank you very much.